So this is lesson 3 of where we are going to talk about circular motion, which is a topic in A-level physics. More specifically, we're going to focus on centripetal forces. So before you can understand what is meant by a centripetal force, you first have to understand what is meant by the term tangent. So what is a tangent? So a tangent is simply a straight line that touches a curve or the circumference of a circle at one point. So when the concept of a tangent is applied to circular motion, which is literally an object moving in a circle, and the key word being motion, that straight line becomes the direction of motion for an object, but only at a particular instance. So a key property of a tangent is that its direction of motion at that particular instance is perpendicular to the radius of the circle. You can use the term perpendicular or at right angles or at 90 degrees, they mean the same thing. But remember that the tangent is not perpendicular to the direction of motion. The tangent is the direction of motion, and that direction of motion is perpendicular to the radius of the circle. So imagine swinging a ball on a string. Let go of that string. The ball flies off in a straight line. And that straight line, that is the tangent. So now that we understand what is meant by the term tangent, what is meant by the term centripetal force? So a centripetal force is simply a resultant force that acts towards the center of a circle when an object moves in circular motion. In simpler terms, when an object moves in a circular path, there's a force that acts towards the center of the circle, and that is the force that keeps the object in a uniform circular path. The reason why it's called a resultant force is because the forces acting on the object are unbalanced, meaning it is the net inward force acting on the object. As previously mentioned, an object moving in a circular path is said to be accelerating due to its constant change in direction, even if its linear speed / actual speed is constant. So in other words, a centripetal force is the force that keeps an object moving in a circular path, and it acts towards the center of the circle, or you can also say a curve. So now let's have a look at a few real-world examples of centripetal forces in action. So when a car turns a corner or is moving in a circular path along a roundabout, it is the friction between the tires and the road which acts as the centripetal force acting towards the center of the circle, keeping the car in uniform circular motion. And when a planet orbits, for example, the Sun, gravity acts as the centripetal force acting towards the center of the circle and keeping the planet in uniform circular motion. So when an object is being spun on a string, such as a ball, it is the tension in the string which acts as the centripetal force acting towards the center of the circle, keeping the ball in uniform circular motion. And a roller coaster loop is when things get a little bit more tricky, but the concept is the same. This is where, depending on the position of the roller coaster, the normal contact force or gravity, or both, act as the centripetal force acting towards the center of the circle, keeping the roller coaster in uniform circular motion. Okay, so now let's look at what is meant by the term centripetal acceleration. Centripetal acceleration is simply acceleration an object experiences when it moves in a circular path, and it acts towards the center of the circle. As mentioned previously, acceleration doesn't just mean if an object speeds up, It also means if an object slows down or changes direction. So when an object travels in a circular path, it's constantly changing direction, meaning it's accelerating, and that acceleration is directed towards the center of the circle. So now, a key point to remember is that centripetal acceleration does not change the speed of the object, only its direction of velocity. And that centripetal acceleration always acts towards the center of the circle. So if a centripetal force and centripetal acceleration both act towards the center of the circle, what is the difference between the two exactly? Well, the key distinction is that centripetal acceleration arises from a centripetal force such as tension, gravity, or friction, depending on the type of uniform circular motion as mentioned previously. In other words, centripetal force is the cause and centripetal acceleration is the effect. Now, let's take a look at an example to help clarify the distinction between centripetal force and centripetal acceleration. As mentioned previously, when a car moves in a circular path along a roundabout, it is the friction between the tires and the road that acts as the centripetal force, which acts towards the center of the circle, keeping the car in uniform circular motion. Centripetal acceleration then arises from that centripetal force, which also acts towards the center of the circle. So now let's have a look as to how do we calculate centripetal forces. Yeah, let's have a look how we calculate centripetal forces. One equation to calculate centripetal force one equation to calculate a centripetal force is F equals mv squared over r. In other words, centripetal force equals mass times by velocity squared over radius. So another equation we can use is F equals mass times by omega squared times by radius. In other words, centripetal force equals mass times by angular speed squared times by radius. Remember that angular speed is measured in radians per second. And how do we calculate centripetal acceleration? So there are two useful equations that we can use to calculate centripetal acceleration. First one is A equals v squared over r. In other words, centripetal acceleration equals velocity squared over radius. And the second is A equals omega squared r. In other words, centripetal acceleration equals angular speed squared times by radius. So now we're going to address a common misconception. So one misconception to address is the term centrifugal force. Centrifugal force is not the same as centripetal force or centripetal acceleration. Centrifugal force is actually a fictitious force that appears when motion is analyzed from a rotating frame of reference. In an inertial / non-rotating frame, there is no outward force acting on the object. The object simply continues in a straight line due to inertia, and the inward centripetal force is what changes its direction. However, if you analyze the motion from a rotating frame, for example, from inside a spinning ride, an outward force appears to act on you. That apparent outward force is what we call centrifugal force. It's not a real interaction like tension or gravity or friction. It only appears because the reference frame itself is accelerating. So one more time, it's not a real interaction force like tension, gravity, or friction. It only appears because the reference frame itself is accelerating. Okay, so now let's have a look What is meant by the term tangential speed and how does it differ from linear speed? So, linear speed is an umbrella term. It's simply speed, which is a scalar quantity, without taking into account direction. Tangential speed is linear speed. Tangential speed is linear speed applied to uniform circular motion, and it acts along a tangent to the circle. One more time. Tangential speed is linear speed applied to uniform circular motion and acts along the tangent to the circle. Okay, so now let's have a look. So if an object moving in uniform circular motion is accelerating because it's constantly changing direction, how do you calculate the distance that an object has traveled? If you use the tangential speed and motion of the object at one particular point, you can simply use the speed equals distance over time formula. You can simply use the speed equals distance over time formula. Therefore, you can use the formula L equals v times by delta t. In other words, distance equals velocity times by time. The distance here is the distance the object has traveled along the circular path, and velocity is tangential speed, and time is simply the time taken to complete the distance traveled. Another way to calculate the distance traveled by an object moving in a circular path is using the equation S equals r theta. In other words, distance equals radius. Distance equals radius times by theta, where S is the distance traveled along the arc, r is the radius of the circle, and theta is the angle moved in radians. So here we take into account the angle the object has moved along its circular path, and we measure that angle in radians. So between 2 points A and B along a circular path, how do we calculate the change in velocity for the object? So we can simply use the equation delta v equals v at point B minus v at point A. In other words, change in velocity equals velocity at point B minus velocity at point A. Here, even though the speed is constant, the velocity vector is different because direction has changed. Another way to calculate the change in velocity between 2 points, such as A and B, is by forming an isosceles triangle. So, how can an isosceles triangle be used to calculate the change in velocity of an object moving in uniform circular motion between 2 points such as A and B? So this is because isosceles triangles have two sides that are the same length, and linear velocity is always tangent to the radius. So in simpler terms, if we use O as the center of the circle, the velocity triangle is similar to AOB because velocities are perpendicular to the radii and subtend the same central angle. So they have two equal sides which equal their velocity, and the angle between them can be used using the cosine rule to calculate the third length, which is the change in velocity. Okay, so now let's have a look. So what if an object moving in uniform circular motion is moving at an angle? Here we can divide the forces acting on the object into two parts: its horizontal component and vertical component. So for example, a car turns a corner along a banked road. So here, the normal contact force can be divided into two parts. The horizontal component of the normal contact force acts as the centripetal force, whereas the vertical component of the normal contact force balances the weight of the car, which also acts as a vertical component, of the forces acting on the car. So how about an aeroplane traveling in a uniform circular path but at an angle? Here the lift force can be divided into both horizontal and vertical components. The horizontal component of the lift force acts as the centripetal force, and the vertical component of the lift force balances the weight of the aircraft, which is also a vertical component of the forces acting on the aircraft. Therefore, there is no vertical acceleration in both scenarios. So another example is a conical pendulum, which is simply a stone attached to a string and whirled in a horizontal circle. So here it is the tension in the string which acts as having both a horizontal and vertical component. The horizontal component of the tension in the string acts as the centripetal force, and the vertical component of the tension in the string balances the weight of the stone, which also acts as a vertical component of the forces acting on the stone. And once again, there is no vertical acceleration. So as you can see, the pattern is very similar. The horizontal component provides the centripetal force, and the vertical component balances the weight of the object, and there is no vertical acceleration. So lastly, we're going to look at one more example. So this is about a fairground ride where a cylinder spins and riders have their backs against the walls of a cylinder. So there is no angle here actually, so we're not going to refer to the forces as components. So here the key to understanding how the vertical and horizontal aspects of the forces acting on the riders are measured is that the floor drops away, meaning there is no normal contact force from the ground. So here, horizontally, the normal contact force acts from the wall, which acts as the centripetal force, keeping the riders in uniform circular motion. And the vertical forces acting on the riders are the weight of the riders, which is balanced by the frictional forces from the wall, which act upwards. Okay, so that's all for lesson 3 of circular motion, and take care and goodbye.